Hey guys, so today I'm going to be doing another LeetCode Daily Challenge. And let's get started. Minimum cost walk in weighted graph. There is an undirected weighted graph. With n vertices labeled from 0 to n minus 1, you are given the integer n and an array edges where edges at I is equal to ui, vi, wi indicates that there's an edge between u to v with a weight of w. A walk on a graph is a sequence of vertices and edges. The walk starts and ends with a vertex, the edge, and each edge connects the vertex that comes before it and the vertex that comes after it. It's important to note that a walk may visit the same edge or vertex more than once. The cost of a walk starting at node U and ending at V is defined as the bitwise AND of the weights of the edges traversed during the walk. In other words, if the sequence of edge weights encountered during the walk is 0, 1, 2, then the cost is calculated as 0 and, okay, where and denotes the bitwise AND operator. You are also given a 2D array query where for each query, you need to find the minimum cost to the walk starting at vertex Si and ending at Ti. If there exists no such walk, the answer is -1. Return the array answer. Okay, so that's a lot of stuff, and also it's a hard problem. I haven't done a hard problem in a long time. I usually don't do hard problems just because, um, I don't know. I mean, I don't think that I'm that good at LeetCode, right? So I could like barely do these medium ones, so I don't really touch the hard ones. Um, but I guess it's good to start. Anyways, this is obviously some sort of graph problem, right? Some sort of graph problem. Um, I think when we see costs and like weights and stuff, you that's usually like a Dijkstra's algorithm would work here. Um, but I don't know about like the queries. Oh, what I mean by the queries is we just traverse all the queries and run Dijkstra's for each query. That doesn't seem like efficient though. I don't know. Let's see. To achieve the cost of 0 in the first query, so the query is 1 to 2. They want from 1 to 2. We need to move on the following edges: 1 to 2 with a weight of 1. So we want to go here. We a different color. So they want us to take this, and then 2 to 1 with a weight of 6. And then back to 2. So that's going to be 1 and 6 and 1. one ANDed with this ANDed with that gives us a cost of 0. Wow, that's tough. That's interesting. So if the query was they want to get from 0 to 3, the best way to do that is with a weight of 7 like this, then a weight of 1. Oh yeah, and then you just go backwards. One, two, three. Hmm. Okay, I don't think I would be able to do this problem on my own, but some idea that I have is that um, since we're given like some sort of graph, right? And there's no restriction on how many trips we can make. They're just looking for the minimum cost, right? So usually with these problems, it's like, oh, it would be inefficient if we go like from here and then go here and then maybe go back and then maybe like go back again, you know. But I think for this one, it's actually encouraged. Um, hmm. right? I might not be understanding it correctly, but I think we're allowed multiple graphs or multiple connected components, right? Just like in example one, where the four is like somewhere else. So I think we could even have something like this, right? Like that's possible. So I think you probably want to like pre-compute. Okay, yeah, I'm definitely not going to be able to do this one. But if I had an idea, maybe we could pre-compute the connected components to try to find a zero. Because once we find some sort of zero out of all of these, then any node, like if you want the minimum, what is it called? The minimum cost walk to get from any of the components in the connected, any of the nodes in the connected component, the minimum is just going to be zero, right? And it doesn't matter if you like it doesn't matter what order they're anded in. So I think the whole goal with these connected components is, can we at least just look through every single option? Like what happens if I just and everything? It should be zero, right? Yeah, it should be zero. So similarly, if I don't care about the exact route I take, what if I just did 7, 7, and 1? Because I'm assuming like I'll just visit all of those. So 7 and 1. If the minimum is um what's the minimum? The minimum might be 1, right? Yeah. Okay. Okay. So maybe this is more of a connected components type problem. We want to and all the edges of that connected component. And then the only thing I feel like it's possible to, how do we determine if two nodes are part of the same connected component, right? Do we need some sort of like representative type thing? I feel like that's a thing, but I don't have a lot of knowledge on that. And then we'll just need to store the min of each connected component. Oh, but what if you're anding? Okay, so then actually that might not work, right? Because what if this was like a 1 and they wanted you to get from 1 to 2, but then this was like a 3. If you anded everything, right? If you printed these ones, I think if you and everything, it would be a 3. No, you get a 1. Yeah, actually, I don't know. I'm just gonna go off that, like anding all the edges of that connected component. I'm gonna make this claim, this bold claim that if we and um, all the weights of a connected component gives the min cost. Store the min of each connected component. And then we just need to loop the queries to see if they are part of the same connected component. So we can have a graph, right? And then what this graph is, it's going to have the source to the destination with the weight. UVW for UVW in edges, the graph at U dot append. So the key is going to be a node ID, and the value is going to be a list, and inside that list it's going to have the node V. Sorry, I guess this is a node U. The list is going to be node V with the weight, right? So we want to append node V with the weight. And then since there's no direction, we can make the same connection back. V goes back to U with the same W. Print the graph. Let's just see what this set does for now. Okay, 0 points to 17, 1 points to 07, 1 points to 37, yep. And then 1 also does the 2, 1, yep. 3 goes to 1, 7, yep. 2 goes to 1 with a weight of 1. Okay, so I populated the graph correctly. How do we keep connected components together. N is 5, so used is going to be 0, 1, 2, 3, 4. Yeah, used is going to be false. Okay, yeah, I really don't know what I'm doing, but now I'm going to try to make representatives for different connected components. Like for example, if we took this one, let's just say there was more, like there was more stuff here, like this was a 5, and then maybe it even connected to a 6 right here. So we could see that there's two connected components. One is right here, and another is right here. So I kind of want to like name them something. So I think what I'll do for node in range n, so we're going to loop all the nodes, right? 0 through, if there's 0 to 6. If used at node, if it's already been used as a representative, then we can just continue. Otherwise, we haven't seen it yet. So in the beginning, we haven't seen it yet, and we start at 0. Else, let's default ticked int, where the key is going to be the node, and the val is going to be its representative. Wait, maybe here is where I could just say BFS, call BFS, with a like starting node, which is this node, sorry, which is this node. And if whenever we call BFS on the node, then this also acts as a representative. So maybe I could do that as well. Okay. Def BFS, give me the source. Source is the starting node as well as the representative for this connected component. Q is a deck starting with the source. Visited is a set that has the source. Curve representative is the source. While Q current node is Q pop left. Let's set the rep, right? So current node, so the representative of this current node is going to equal the current rep. And then we just look at the graph, right? So for neighbor in graph of the current node, if nay not in visited. Q dot append the neighbor. I think that's it, right? And then do we return anything? I don't think we return anything. We just do that. And also now that I think about it, since I'm running BFS, I might as well and everything, right? So I could maybe return something. Maybe I could return the min cost, which I haven't wrote a proof on that, but I think min cost is just adding everything up. So I'll just have a running add is equal to whatever source is. No, 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 no. Wait. What if it has multiple routes? I don't know. I guess that's another thing for later is what do I return? Because it'd be good to just return the and of everything. I won't worry about that right now, I guess. Doing this was already enough, like setting the representative. Okay. After we set the representative, let's do used at node is equal to true. Oh, now that I think about it, when we call BFS, maybe we could just do the used. We don't need visited. So I would just do used at source is true. For neighbor, if if used at nay, if it's not used, then go ahead and do that. Then go ahead and say use nay is now going to be true. Q dot append nay. Okay. So after I call BFS, let me print the rep, I think would be best. Print the rep, which will give me the node and the connected component representative that it falls in line with. Let's go. Yeah, so it's it's the neighbor and the weight, right? But we don't really care about the weight, so I'll just do this. Okay, so 0 is part of the 0 group. Oh wait, what? Wait, example 1 is the one with like 4 is somewhere else, right? Okay. Yeah, so this connected component right here has a representative of 0, and this connected component has a representative of 4. If I added more, I think that would be good. Let me try adding more. Maybe I had 7 of them, and then I had 4 to 6, 1, as well as 4 to 5 for the 5, maybe. Let's print this out. So we should see 0, 1, 2, and 3. We should see nodes 0, 1, 2, 3 all have a representative of 0. Zero, 1, 2, and 3 have a representative of 0. And we should see 4, 5, and 6 have a representative of 4. 4, 5, 6. Okay. Okay, that's fine. So I think I could answer one part of this, right? So we definitely need to do for, what's the queries? S and T, right? So for S, T, and query, for ST and query, if the rep of S does not equal to the rep of T, then we could do, we'll have a result as a list, right? Then our result dot append -1. Also, for now, I'm just gonna say result append maybe a 0. Let's just run this for now, just to make sure. Oh, return my result. Don't need to, okay, let's do that. Okay, yeah, so I'm outputting a -1 when I should. Like, if two nodes are not even in the same connected component, I'm putting out a -1, which is good. And then the zeros are just there just because I haven't processed those yet. Okay. Okay, so far so good. Sorry, this is learning experience. Okay. So now that I think about it more, if I'm calling BFS, I should at least be trying to also get the and of everything. I might as well, right? So that's something I need to focus in on as well. How am I going to do that? Um, I think I could have like a side thing where um, maybe I could have a visited and it's going to be a set, but inside of the set, it's going to have it could just have the triplet, right? Like um U, V, and W. Or maybe I could run a completely different BFS to do that. So I want to visit all the edges. Uh, Actually, I know all the representatives, right? Let me just print out the representative um, dot values. There should only be like two. There should only be like two of these, right? Because we just there's only like two connected components. Oh my gosh, what am I doing wrong? Oh, let me just pass this for now. Oh, representative dot values, but as a set. So how many different connected components do we have? They're going to give us this to us. We have 0 and 4. And then I think we could just loop through that. Um, Maybe I could have a running and. It's just going to be a default dict. And it's going to have an int where the key is like the representative and the value is the running and. It's just anding all of the weights together. So all we need to do is just look through the queries one more time. I mean the edges, right? For U, V, W in edges. The running and. Running and of U. Of the rep of U, the representative of U wants to be anded with W. The only thing is if I have a 0 anded with anything, it's just a 0. So how do I flip the 0? Is it tilde 0? Oh, I guess. Um, I want to and it equals with W, but what's the starting value of the running and? It's kind of annoying. Because I think it's a zero, right? And anything ended with a zero is just zero. Which means I just need a scene. Maybe could be a scene set. Or I could do false times n again. For current rep in set rep dot values. If the scene at there is going to be true, if graph, if the length of the graph at if the length of this is greater than 0, running and at there is going to be equal to graph CP, which is going to, so graph CP is going to give us this, right? And then we want the weight, so that's at 1. I think that's how it works. And then for this, we just and it with W. Let me print out the running and. Let's try this. This is crazy code. This is not gonna work. Oh, I think okay, I think to access it, sorry, it's 0 to get the first element, and then we want the second part of that list, which is the weight. So it's 0, 1, like that. I think that's fine. Run that. Okay, so what's our running and? Wait, I don't care about the rep anymore. Just give me the running and. Okay, okay. I think this is good, right? So wait, case one was this. And 4 didn't have anything, so we totally ignore 4. But then it says the representative at 0 has an accumulative and a running and of 1, which is exactly what we wanted, right? Let's look at another example. For this one, 4 6 has a 1, and then 4 5 5 has a 5. So 1 2 4 ANDed with a 1 is just going to give us a 1. So we're expecting a 1 right here as well, which we do have. Okay. Okay, let's try that. So get the min of the connected component, which has already been processed, right? Res.append. It's just the running and of the representative of whatever is at that node S or T, it doesn't matter because they're connected, right? And then that's it. Okay, let's submit. Oh! I'm so stupid, but that was fun. That was pretty cool. I'm so stupid though, but that was cool. Damn. No way that's the intended way though. Did I just cheese the problem? Probably. But damn, that was so cool. Anyways, okay. So now that this is correct, what was it? Was it good? Damn. Okay, what did I end up doing? I ended up, so first I noticed that there can be multiple like islands, right? There could be multiple connected components. And then I guess it's true that if we and everything, we'll always get this like the smallest. Huh. Yeah, if we and everything, we'll get the smallest. Um, yeah, there's a proof in there somewhere, but something I could think about is like if you think that all the zeros and then the 1 is good, and like that might be the smallest, then it would be no problem, right, to and it with something really big. Because if something was really big, like a bunch of 1s right here, if you anded this, you would still just get that smallest number. So if there's anything that is really small, it actually helps us. So to get the smallest, we could just and everything in the connected component. Well, to do that, we first need to separate all of the islands. And in order to separate the islands, I kind of ran, well, first of all, you need to create a graph, right? To represent this, you need to represent it as a graph. Then you need to kind of like go through each of the node and say, hey, is the node used? As in, we're ready to assign a representative to the island. And if the node has not been used, that means this island has not been explored yet. So let's go ahead and explore the island we call BFS. So in the BFS, that's where we run BFS on the island and we assign the representative to that source node right here. The rep of the current node is equal to the current representative. Now we do that for all the islands, right? And then now that we already have that, we could just and all the weights per given island. then we can just run through the query and check to make sure that before we just do like the running and of the rep, we just need to make sure that the destination, like S to T, is part of the same island. If they're not part of the same connected component, we just put a -1 right here. If they are part of the same connected component, we can either do rep of S or rep of T. It doesn't matter, right? They have the same representative. And then we just want the running and, which is calculated above. And then we just append that to the result. Okay. Yeah, so that's all I have today. I think it's just ON. I'm not sure. I'm not good with the time and space complexity of these graph problems. I need to like look up on that. But yeah, thanks for watching. That's it.